Welcome to another lecture, Lecture 6, Under Reinforced and Over Reinforced section. In this lecture, I will discuss how to calculate the area of steel or reinforcement ratio for the under reinforced and calculate the neutral axis depth in under reinforced and in the over reinforced section. Under reinforced failure. How under reinforced failure occurs? Stage 1 Uncracked section. Neutral axis position is fixed, means LA remains unchanged or constant. Only T and CC increases with the increase of load. Means there is no tension cracks on the first stage. There is no tension cracks on the tension phase. And in that case, neutral axis position will be remain same. Only T and C increases with the increase of load. Now second, when these cracks start developing on the tension side. When section cracks, neutral axis moves towards the compression phase, means LA start increasing. Okay. T and CC also increases with the increase of load. That is the second stage. Third stage, yielding in steel. Load keep on increasing until steel starts yielding. And after yielding of steel, concrete crushes. T as Fy is the tensile force remains constant and Cc also remains constant. La increases as the neutral axis moves towards compression phase because cracking continues. As cracking continues, the neutral axis start moving towards upward. As a result, La will also increase. Now the result, failure initiated by the yielding of steel, but final failure is still by the crushing of concrete. Okay, that's the under reinforced failure, the philosophy. Failure initiated by yielding of steel, but the final failure is still by the crushing of the concrete. Means first steel will yield, then concrete crush. How? Under reinforced, that's the basic moment capacity formula, that is we have seen in the previous slides. That is phi b is the strength reduction factor in bending, T into La, tensile force into La. T is the ASFY into D minus A by 2. That is, we already know. And we also know what is the value of A in the tension control section and under reinforced failure. For tension control section 0.9, and the value, I have put the value 0.9, and A is ASFY divided by 0.85 FC prime B. Okay, I will put the value of A into equation 1 here after putting the value. Okay, 2 is there, all the equation of A put in 1. Okay, now the result is here. Okay, now I am changing AS into rho BD. Okay, we already know reinforcement ratio is area of steel divided by BD. Okay, same here, same here. Okay, now I am taking common. Now I am taking common D from this side, from this side. Okay, and this B from downside, B from upside will be cancelled. For economical design, the moment capacity will be equal to applied moment. Okay, equal to applied moment, and this will equal to this, and 0.9 rho B D square. D is taken common from this equation. Now 1 minus rho Fy, because B and B already cancelled. Okay, so from BD square from this side taken from the taken to the other side. Now this will our next result of the equation. Now for simplification, let take mu over BD square equal to R and 0.85 Fc prime over Fy is equal to omega. Okay, so then mu over BD square will become R and 0.85 Fc prime over Fy will become 1 over omega, because this is downward. So this is a new equation. Okay, now to get the value of rho, okay, so here I am taking 0.9 Fy to the other side, rho is here. Now after multiplying, rho minus rho square over 2 omega. Okay, now 2 omega multiply on both sides. This is the result of this is resultant in the of rho in the form of quadratic equation. Okay, for further simplification, I am multiplying and dividing by 0.85 fc prime over 0.85 fc prime with this value. Okay, and 0.85 fc prime our fy will become omega, then this will become omega square, and downward I will 0.9 multiplied by 0.85, then divided by 2, this value will come. Now putting in the quadratic equation, rho is equal to, this is minus, so that's why there is positive, minus b plus minus b square minus 4ac divided by 2a. A is 1, so that's why this is. After simplification, this value will get for the rho, for the reinforcement ratio. Okay, so there are two values, positive and negative. We use the negative value because for under reinforced section we will use the negative value. Why? For under reinforced section, reinforcement ratio should be less than rho balance for tension control section for under reinforced. If we use positive sign of rho, rho will become greater than rho balance, leading to brittle failure. That is, we do not want. Now again putting back, here is the result of putting back the again values of omega and r. Omega is this, r is this. Okay, the net result will become this. Omega is 0.85 fc prime over fy, 1 minus under root 1 minus 2.614 in the place of r, mu over bd square. This is the reinforcement ratio for the under reinforced section. If we have a moment, applied moment in the beam, then we can calculate the reinforcement ratio for that section. Okay, if we have the reinforcement ratio, as we know, reinforcement ratio is area of steel divided by BD, then we can get the area of steel. How much area of steel is required in that section? Rho will be multiplied with BD. Now that is the second method for the determination of area of steel. That is the hit and trial method. In the trial method, assume some value of A. For example, tentative value. For example, D by 3 or D by 4 or any other reasonable value, and put in the equation C. Okay, when we put the value of A into C equation, then after that we will get area of steel. Then we will put that area of steel again in the trial 2, put in this equation A, and then we will get in A to get a value of A. After getting the value of A, put this A value into the equation C. Then you will get again the value of area of steel. You will do this process until the area of steel start merging to one point. Keep on doing the trials unless AS from a specific trial becomes equal to the AS calculated from the previous trial. This value of AS will be the final answer for the calculation of area of steel for this section. Now the next is the check is the section is under reinforced or not. If the reinforcement ratio is less than rho maximum, then section is under reinforced. Second way, using A and D, calculate strain in steel. If strain in steel is greater or equal to 0.005, section is under reinforced, means tension control. If the section value is if we put the values and in the under road we get the negative value, it means the that is over reinforced section, it's a compression control. Okay, that is the check of under reinforced is not the section is under reinforced or not. For tension control, tensile strain 0.005 and A is beta 13 by 8D. The moment capacity formula we already know, phi C into LA. Phi C value is here 0.85 Fc prime BA, and this is a lever arm. Okay, now I will put the values of A, where A is in the equation. Okay, at this place and at this place. After simplification, I will get this value. Okay, here you will take all the values on the other side and take the D. This D minimum is the minimum effective depth required that for under reinforced section. If your section has a D value greater than this D minimum, then your section is under reinforced. If we keep D our effective depth of section greater than D minimum, the resulting section will be under reinforced. Okay, if D is greater than D minimum, that means section is stronger in compression. Okay. Now, for the over reinforced failure. For the over reinforced failure, the first two stages are same. Means in the first stage, LA remain unchanged or constant. CC and TT will increase with increase of load. Similarly, in crack section, when the cracks start appearing, the CC and TT will also keep on increasing, but LA start increasing. In the third stage, that is different in the over reinforced failure, concrete reaches strain of 0.003 but steel not yield. In the over reinforced failure, steel will not yield. The failure will be the failure of concrete on the compression side. We never prefer design a beam as over reinforced, as it will show sudden failure. Okay, when sudden failure will appear, when concrete crush but steel will not yield. Okay, now the calculations. Concrete reaches to that strain value but still not yielding. Here is 5b mn cc into La. 5b mn 0. That is compression failure. Okay, that's the factor is 5 0.65. 0.85 fc prime ba d minus a by 2. Okay, a is unknown as fs is not known. Okay, here a is as into fy when steel is yielding, but in this case steel is not yielding because stress level is less than the yield stress. That's why it's the values fs. Okay, 0.85 fc prime over b. So now first calculate fs, then we will get the value of a, then we will get the capacity of moment capacity. Here is a similar triangle, okay, comparing ABC and ADE. Okay, here is 0, here is strain S. Okay, similar triangle. You can compare perpendicular over perpendicular, base over base, or here base over base, strain S over 0.003, D minus C over C. Okay, put the value of C as A over beta 1. Okay, after simplification you will get this value. Okay, now stress over strain is equal to modulus of elasticity. Stress over strain is equal to modulus of elasticity. Now I will multiply with strain S with modulus of elasticity. The value will be 600 beta 1 minus A over A. Now I will put this equation again back here. I will get the value of A. Okay, here I have put the value of Fs in the equation and get the value of A. And now you can see A is on the left side and A is also on the right side. After solving this, we will get the quadratic equation. Here the result after solving this equation. You will solve this equation. If you face any issue, you can ask the question at the end. Okay, so after getting the value of A, you will put in the basic equation 0.85 fc prime ba into d minus a by 2. When you can use compressive force, or when you are using tensile force, you can use A as Fs, not Fy, d minus a by 2 for calculating the moment capacity. Okay, this is summary of all the discussion. For the extreme tensile strain, if that is less than yield, that is compression control failure. If that is greater or equal to yield, then that will be transition. If this value is greater than or equal to 0.4, that is under reinforced but transition. And if your strain values are greater or equal to 0.005, then that is the tension control. All the values I have discussed in the previous lectures, that is just the summary. For example, compression control 0.65, for tension control 0.9, and for the transition you have to interpolate. Rho maximum value for tension control, for compression control, similarly for transition. A and A over D values we have also discussed in the previous slides. So that's all for today's lecture. Have a nice day.